Hello everyone. In this lesson, we continue to study the content of the first chapter, Analysis Method of Crystal Diode Circuit. In the previous content, we have understood the internal structure of crystal diodes and related characteristics. What we will analyze in this lesson is that if the diode is placed in the circuit, what method can be used to solve its voltage and its current. The analysis methods are usually the following. The first is computer-aided analysis, which uses the mathematical model of the diode. The second method is graphical analysis, which uses a curve model. The third method is called the equivalent circuit analysis method, which uses the equivalent circuit model. Among the three methods, we use the most or frequently used is the third method, so this is also the focus of our lesson. Before talking about analysis methods, let's first understand the various models of crystal diodes. The first is a mathematical model. When we explained the p-n junction, volt-ampere characteristics before, we already know the current and voltage of the diode, which can be described by the formula of exponential rate. This is the ideal model. In the actual calculation, this formula needs to be revised. I is equal to Is times the brackets E minus I multiplied by Rs, and then reduced by 1 times the Vt of n times minus 1, where n is a non-idealization factor. When the current I is normal, n is approximately equal to 1. If I is too large or too small, n is approximately equal to 2. If you consider the diode body resistance and a lead contact resistance, then Rs cannot be ignored. This formula is usually used in computer-aided analysis method to solve its low voltage current. We generally use this method and rarely use it when analyzing circuits, so it's not important. The second model is a curve model, also called volt-ampere characteristic curve. Volt-ampere characteristic curve can be measured by experiment. In this curve, VD on is a dividing point. When V is greater than VD on, the diode is turned on. We think the relationship between their current and voltage is an exponential rate relationship. When V is less than VD on, the diode cut-off current is very weak. The volt curve can be used to solve the voltage and current of the diode. By drawing, we draw the volt-ampere characteristic curve, and then draw the outside of the diode tube, this load line of the circuit, to find the intersection. By reading the coordinates, you can find its voltage and current. We usually do not use this method. Let's look at the third model, called the equivalent circuit model. Let's take a look at the actual circuit of the diode. The picture on the left. In the picture, the power supply is DC power supply VDD, and the other is the AC signal Vs. There is also a resistor RD and diode D in the circuit. If we take the AC signal Vs in the figure, remove or short it, at this time, only DC power supply VDD was used in the circuit. This circuit is simplified to its DC path. In the DC path, we can solve the DC voltage Vd of the diode and its DC current Id. This is called DC analysis. Then, if we put VDD, which is a DC power supply, let it short circuit, keep Vs and only Vs will supply power in the circuit, and the circuit becomes its AC path. In the communication channel, we can solve the AC signal Vd and Id of the diode. This is called communication analysis. During the DC analysis, we usually use a simplified circuit model to describe the diode. The simplified circuit model can be divided into three types. Let's look at the top one first. The so-called simplification is that the diode's volt-ampere characteristic is a curve. When V is greater than VD on, the exponential rate rises. Then we can use a polyline to approximate equivalent to such a volt-ampere characteristic curve. Then the part where V is greater than VD on is a straight line, and we can simplify it to resistance RD, which means that the diode has an internal resistance RD. Then the diode also has a conduction voltage VD on. We use a constant voltage drop VD on and R in series to describe. The diode also has a unidirectional conductivity. We can use an ideal diode, that is, a switch to describe its unidirectional conductivity. When the voltage V across the ideal diode is greater than 0, the diode turns on. When V is less than 0, the diode is turned off. In this case, a diode is simplified to the circuit from described in this figure. The RD, VD on in it, is a circuit component we are very familiar with, including switches, so it is very convenient to analyze. This model is called the polyline equivalent model. In the process of analyzing the problem, it may be further simplified. For example, the resistance outside the diode tube is far greater than its internal resistance. Then we can ignore RD. When V is greater than 0, it can be described by such a polyline, its volt-ampere characteristics. So the circuit form is the circuit form in the picture on the right. That is an ideal diode series constant voltage drop VD on. This is called a constant voltage drop model. That can be further simplified. That is, the power supply and resistance in the circuit are much greater than the diode's turn-on voltage, and its internal resistance RD. In this case, its turn-on voltage and RD can be ignored. Then we can use such an ideal switch to describe the diode. This is called its ideal model. As for which model to use in the analysis, it depends on the specific circuit form. Let's look at the small signal circuit model again. The so-called small signal circuit model is that the diode is for AC small signal. What kind of circuit model is it? What kind of circuit model can we use to describe it? Look at the volt-ampere characteristic curve on the left. The actual DC operating current of the diode is a Q point, and its coordinates are the DC voltage and current of the diode. Assuming that on the basis of the DC voltage, an AC small signal delta V is superimposed, then the voltage is at a Q point, changed within a very small range. We can imagine a small range above and below the Q point. Volt-ampere characteristic curve can be approximated as a straight line segment. AC voltage and AC current, the relationship between delta V and it is a linear relationship, so it can be regarded as a resistance. The diode is seen as a resistor. We define its resistance as Rj. The slope of this curve at point Q is 1/3 of Rj. We can solve this slope. 1 over Rj is the derivative of current I to V, the derivative value at Q. Substitute the expression of I into, we can find the derivative value. It is equal to IQ divided by VT plus IS. IS is much smaller than IQ. IS is a reverse saturation current. So in this case, we can further and make it approximately equal to IQ over VT. I can find Rj, which is approximately equal to VT, ratio IQ. In this case, the equivalent of the diode, the AC resistance can be obtained by the DC current IQ. Because VT can be regarded as a constant of 26 microvolts at normal temperature. For AC voltage, delta V and AC current delta I, the diode can be simplified to a Rj. Such a form of circuit resistance, in some cases, if the series resistance Rs of the P-in junction is considered, its small signal circuit model can be described in the form of the middle circuit. That is Rs series Rd. If the diode is working at high frequency, then Cj can also be connected in parallel across this Rj, such a capacitor to describe its small signal circuit model. Okay, we will talk about its various models here. Okay, thank you everyone. The content of this lesson is here.